new vector functions, what we learned so far? We learned about a vector function, v of t, representing the position of a particle, f of t, g of t, and h of t. Since we have a function, we said that, hey, we have the domain of that function. By finding the domain of each of these components or scalar functions, we can find the domain of this vector function. Then we actually found the limit of the function. We said that the limit of the function exists if the limit of each of these scalar functions exists as well. We talked about continuity. This function is continuous if the limit of the function is equal to the value of the function at the given number. Okay, then we talked about the derivative of the function. When we talked about the derivative of the function, we talked about the tangent vector. And after we talked about tangent vector, which is tangent to the curve or space curve of that function, we say that we can scale that and we have unit tangent vector. Well, some properties for the derivative of the function. Let v, write r, u and v. So let u and v of t be vector functions. And suppose they are all differentiable functions, c is a scalar and f is a real valued function. These functions are differentiable in their given domains. C is a scalar or a number, and f is a real valued function. We have the following properties. The derivative, or if you differentiate the sum or difference of these two functions, u of t plus or minus v of t, it means that we take the derivatives or we differentiate these functions respectively and we add or subtract the results. This is equal to d dt of u of t plus or minus the differential of the v of t. So what if you have the product of a scalar or a constant with your function and you want to find the derivative or take the differential of c times u of t? So in this case, you can just take this constant and write it in front of the differential. C times the derivative of your vector value function. In the case that this is replaced by a real valued function like f of t, and you want to find the derivative, f of t times u of t, this is equal to, we're actually applying the product rule. We say that, hey, we have the derivative of f times u of t plus the function f itself times the derivative of your vector valued function. So what we learned in elementary calculus using the product. So now I take you to ask, what if I have the multiplication of two vector valued functions? So in this case, again, we apply the product rule. The differential of u v is equal to, remember that you have to form the dot product, is equal to the derivative of u dot v plus u times the dot product of the derivative of well, what if we have the cross product between the two vector value functions? Well, so this is number 5. If you have the cross product between u and v, remember that these are all vector functions. It means that we can actually form the dot product and also form the cross product. But how do we take the derivative of the cross product? It is equal to the derivative of u cross v. So the derivative of u cross product v plus, now we were just going to write down u and take the derivative of v plus u cross product, the derivative of v. So in a sense, it's similar to applying the product rule, but note that here we have the cross product between them. And what if we have the composition, the derivative of composition of u and real valued function f? So we have composition of two functions. Composition, it means that we need to apply the chain rule. The chain rule says here it is equal to the derivative of f times the derivative of u composed with f. Okay. Perfect. Well, here's an example for you. This example says, show that if the magnitude of a vector valued function is constant, if the magnitude of a vector valued function is constant, it means that if the length of that vector valued function is just fixed number, it's equal to constant, then the derivative of this function is orthogonal to R. For all t values in the domain of that function. So what is our goal? Our goal is to show that these two vectors are orthogonal. So our goal is to show that R prime and R are orthogonal. So it means that the angle between them is equal to pi over 2. So when the angle is between them is pi over 2, what's the meaning of that? It means that the dot product is equal to 0. But how do we show that the dot product between r and r prime is equal to 0? How do we show that? This is our goal. We want to show this. We want to prove this. We have to start somewhere. Well, so what we learned in this course, we know that, so this is a question mark, this is what we're trying to prove. We know that the dot product between any vector, like v and v, is equal to, so when we're talking about the dot product, it's, remember that, it's like this. You have, for example, 1, 1, and 1, and you find the dot product between these two. How did you define the dot product? It was equal to 1 times 1, 1 times 1, 1 times 1, which was equal to 3. So when you're thinking about this, it means that you are taking the elements of V, multiply them together, and then you find the raised to of square root of that vector. So this is equal to, you can write it this way. This is the magnitude of this vector, like V, raised to the second power. Okay, so equivalently, you can in general write down as magnitude of vector. Raised to the second power. There we go. Very well. So let's see. In general, the magnitude of vector v, which is equal to square root of the dot product of the n. Very good. So what do we know? We know that the magnitude of this vector is equal to a constant like c. Okay. I know that r of t times r of t is equal to the magnitude, which is c squared. You have a dot product between two vectors. You just learned that. You learned that. If you have a differential of u dot product v, we need to apply the product rule, which says, hey, we have the derivative of u times v plus u times the derivative of. But this is what we learned today. So what I'm going to do, I'm going to take the differential of both sides. I get d over dt of r of t dot product r of t, so it equals to the derivative of this constant, which is equal to 0. I already know. But on the left-hand side, what I get the derivative of r times r plus r times the derivative of r, which is equal to 0. The derivative of constant is equal to 0. So what is this? Remember that here I can just change the order. This is equal to 2 times r of t times r prime of t equal to 0. Divide both sides by 2. We get r of t times r prime of t equal to this. What is this? This is saying that, hey, I have two vectors that are orthogonal to each other. Perfect. just learned about fundamental theorem of calculus. If the antiderivative of a function exists, we can define the integral without being worried about the Riemann sum and the things that we learned before. So let R. So this is a function, let R of t be the antiderivative of vector function R of t. Well, we can talk about the integral. So the integral from a to b of vector function R of t dt is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. This is coming directly from elementary calculus, the fundamental theorem of calculus. For example, let R of t be equals to 2 cosine t, comma sine t, and then you have 2t. Question says, find the integral of RT. In general, what is this integral? And what if I ask you to find the integral 0 to pi over 2 of R of t dt? And what's the graph like? So, perfect. The antiderivative of this vector valued function R of t is equal to. So it means that we can just find the integral of 2 cosine t, 2 sine t, the integral of sine, negative cosine t, and the integral of 2t, t squared. So this integral, which is equal to the integral of 2 cosine t dt plus the integral of in the direction of x-axis. So let's start ijk as well. I plus the integral of sine t dt in the direction of y-axis plus the integral of 2t dt in the direction of z-axis. This is just equal to 2 sine t in the direction of x-axis minus cosine t in the direction of y-axis plus t squared in the direction of z-axis. Okay. Or another way to represent this is 2 sine t, the first component, the x component, and negative cosine t, the second component, and the last component is t squared. Now, the rest is not that hard. Just plug in pi over 2 into the vector function there, and then we subtract after we plug in 0. So 2 sine of pi over 2, comma, negative cosine pi over 2, comma, pi over 2 to the second power minus, now we plug in 0, 2 sine of 0, comma, minus cosine of 0, comma, 0 squared. The outcome is a vector. So this is equal to 2, 0, and pi half squared minus 0, negative 1, and 0. You combine these two, the outcome is equal to 2 minus 0, which is 2, 0 plus 1, and then pi squared over